Today we look at Unit 20, Area Computation. Let me remind you, the first thing is a reminder that if you have a function f of x which is continuous here on AB, then the integral from A to B is the area under the curve. If you want to compute this area here, we can just compute the integral from A to B, f of x dx. So for example, if f of x is equal to x squared and A is equal to 1, B is equal to 2, we have this situation, we go from 1 to 2, and we have the graph of the function x squared here, this graph in parabola, and we are looking at this area here, and the area is just the integral from 1 to 2. Then we have x squared dx, and we know how to integrate x squared, right? That's x cubed third evaluated from 1 to 2. Let's move that a little bit away here, and when we look at that, that's 8 minus 1, that's 7 third. So this area here is 7 third. We can generalize this. So we can look at the area between two curves. So if we have, then we have an interval a, b. But now we have two functions. We have a function f of x and we have a function g of x. And if we want to compute the area sandwich between these two parts, this area here, what we can do is we can just look at the area under the curve G and subtract the area under the curve F. That's what you have done in the homework once. So what we have is the area is the integral again from A to B. But now we have just g of x. We would take g of x here, we would get the area under the curve G, and then minus f of x, that's the smaller function, dx. That's what we most of the time use to compute area. For example, let's just take an example. Maybe look at a lot of other examples later, but example is find the area sandwiched between x squared and x cubed. So what does this mean? The area between x squared and x cubed, we have to make a graph. We have to draw the graph of this function. So x squared is the parabola here. So that's x squared. And then we have x cubed, which is here this function. And we know actually here, now we have this, we see the picture, right? We see that this area is what we meant here. So we want to compute this area here. Now you see one difficulty is that we have to find out where these curves intersect. We have to find the interval AB. In this case, A is equal to 0. And we see when they are equal, x squared is equal to x cubed. That means B is equal to 1 here. So we see that with a picture. Always make a picture, then it's clear. And now we can do answer the question. We can say the integral from 0 to 1 of what is above. So now it's important that we see what is above. So the function above is the function x squared, and the function below, that's smaller, that's x cubed. If you're not sure which function is above and which is below, you just pick a point, like here, 1/2, right? That's 1/4 and that's 1/8. So 1/8 is smaller than 1/4. And so the green graph of x cubed is below the graph of x squared. And so we have here x squared minus x cubed dx. And we know how to compute that, right? So this is something, we have x cubed third minus x to the 4/4, and then we evaluate it from 0 to 1. So if you put 1, we get 1/3 minus 1/4. If you put 0, we get 0. So this is 1/3 minus 1/4. Which is, we make 12. This is 1/12. So this area here is 1/12. Okay, let's look at these examples. Let's look at these examples of area computations. So in the first, it's very important that we draw the picture in each of the cases. So in this case, we have two functions. We have x to the 4th, which is here, equals to 0. So this is x to the 4th. That's the lower function, and we have 2 minus x to the 4th, which is the upper function. So we compute the area here sandwiched between these two graphs. There's a little bit of challenge here that we have to find the intersection points. Right? You see the intersection point. We can do that by putting the functions equal. So they intersect when they are equal. So 2 minus x to the 4th. And then we see 2x to the 4th is equal to 2. X to the 4th is equal to 1, which means x is equal to plus or minus 1. So we have minus 1 and 1. And we can write down the integral now. Now it's important that we have to see which one is the upper function here. It's 2 minus x to the 4th. And what is the lower function? Minus x to the 4th dx. So we can integrate this. So this is 2x minus 2x to the 5/5, evaluated from minus 1 to 1. Just put them together. This is 2x 4th, and then x to the 4th becomes x to the 5/5. And so in this case, this is actually just, how much is that? 2 minus 2/5. That's for that. That's 8/5. And then the other one gives the same. So this is 16/5. So that was the first problem. Why don't you just already try to think about this second problem here, the area bound by y is equal to x, y is equal to 2x, and x is equal to 1, while I'm cleaning here the board. It's hard to do that just in your head. So you have to really make a pic. For all these area computations, it's pivotal to make a picture so that we see what is going on, so that we can find out what are the bounds, what is the a and what is the b. We have to integrate over. And so what we have here, we have two functions and the x equal to 1. Which is also a line. So let's just draw all this. So for b. So we have one function which is y is equal to x. It's this function here. Then y is equal to 2x. That's a little bit steeper. Y is so steep. Here, y is equal to 2x, and then we have a third condition which says x is equal to 1. Let's just draw that. So that's x equal to 1. X equal to 1 is is this line here. So now we see what the problem asks. The problem asks to compute the area of this triangle. And we know also the bounds, right? It starts from 0 and ends at 1. So we have from 0 to 1. And now we have the upper function. The upper function is the 2x. The lower function is x dx. So that's the integral from 0 to 1x dx. X squared half, which is 1 half. So this triangle area is 1/2. Now the third problem you might remember from a previous homework problem which we have done. Let me just do that quickly and remind you about this. There's a little caveat here for number C, problem C. You might remember that you might have got 0 as the answer. It is a little bit of a dangerous problem. Like when you have propellers, it's dangerous. you can get hurt. So not with this propeller here. So this is my propeller. So what we have is x to the third, right? X to the third is one function. And the second function which we have given is x. And we ask for the area between these two graphs. And we say we have two blades here. So it's actually, this is one of the blades and this is the other blades. And you might remember we have, if you put them equal here, we get -1 and 1. So now we have the integral, and if you integrate blindly from -1 to 1, the upper minus the lower, x minus x cubed dx, right? You get 0. So that's not the way to do that. And the reason why this gives 0 is because here, you might remember that the function x is above here. This is above the function x cubed. The graph of x is below here of the graph of x cubed. So there's a switch of the order. So this is a positive and this is a negative contribution. So that's not how we do that. And one way to do that is you just do twice this. So by symmetry we can say, okay, this is twice this. And so we have 2 times, and then we have x squared half minus x to the 4/4. And then we evaluate this from 0 to 1. And we get 2 times 1/2 minus 1/4. So this is 1/2. This is equal to 1/4. This is 1/4. This is equal to 1/2. This is an example which we already have done. Good. Now we are launching a more. The next section will be a little bit more difficult example. So this fourth section is completely dedicated to the circle, area of the circle. It's an important problem, historically important, culturally important. It's the start of calculus. Archimedes was doing it. It's a very nice problem, prototype problem. So let's just take the unit circle. So we can write this as just x squared plus y squared, smaller than 1. So this is x, this is y, this is 1. We take the radius 1. And what is this area? Now we can see this problem as a calculus problem because it's the area sandwiched between two curves. Do you see the curves? So we have the upper curve and the lower curve. So we have to find a formula for that curve. For the upper curve, we have to solve for y here. We see that this is y is equal to the square root of 1 minus x squared. So that's the upper curve. And then we have below, we have just a negative. So what we do is we integrate, and we have the bound from minus 1 to 1. We go from minus 1 to 1, and we have the upper function, which is square root of 1 minus x squared. We subtract the lower function, which is just minus, so that actually gives us just 2 times this integral. So in some sense you can also understand it as 2 times the area under this curve here, which is the upper part of the circle, and then we just multiply by 2. Now this is an integral which we don't know. This is we learn a technique to do that later in the course. Needs a clever substitution, and we are not yet there. So I have just to tell you what the antiderivative is here. It's not obvious. So what it is, it's just x times square root of 1 minus x squared plus the arc sine of x. Now, if you are told by an oracle that this is the antiderivative, you can readily check that this is true, right? You just use the product rule to compute here this derivative. We know the derivative of the arc sine, that's 1 over the square root of 1 minus x squared. So it's not obvious, but if you make the calculation, you see that this is actually the right antiderivative. And if you plug in 1 and minus 1 here, we get 0. If you plug 1 and minus 1 here, let's just see, this is the arc sine is a little bit a tricky beast. So we have here the sine function, and we have to look where is the what x value gives us a 1. That's the arc sine. So the arc sine, if you see that it's pi half, so that this is equal to the arc sine of 1 minus the arc sine of minus 1. So the arc sine of 1 is pi half, and the arc sine of minus 1, that's here, minus 1, that's the angle which belongs to that is minus pi half. So it's minus pi half is plus pi half again. So this is equal to pi. Archimedes got that completely differently. We have mentioned this. He actually was cutting things up like this into triangles and computing the area of triangles, exhausting it from inside and outside with polygons. He didn't have that beautiful calculus tool which we have now. So that's the area of the circle. So what we do is we want to compute the following area. Let's just take, maybe take minus 6 to 6. And the function is, it's just the area under the curve. We take the function f of x is equal to 1 over x squared. It's a function which looks like that. It goes pretty fast to 0 here, and then it goes here like that. And we are asking for the area here. What is the area? Well, it's not a big deal, right? What we can do is we can just integrate from minus 6 to 6. We take 1 over x squared dx. And we know 1 over x squared is x to the minus 2. We know the antiderivative of that is just minus 1 over x, right? And this is n. We just add 1, which is minus 1, and divide by minus 1. So this is minus x to the minus 1. So it's minus 1 over x, evaluated from minus 6 to 6. Now we take 6 here, which is equal to minus 1 over 6, and then we subtract here, when we put minus 6, which is, when we put minus 6, this is actually when we put minus 6 here, and we put minus 6 here with this minus sign, and because of the minus which we have to take here, this is minus minus minus, this gives us minus 1 over 6, which is minus 1/3. Anyway, this is a negative area. So you might be worried, you know, that is unbounded here, but it gives us a finite value. It gives us a finite value. Why is this value not right? Now we will cover. Don't worry, we will cover this. Later. This is called an improper integral. So we actually make something forbidden here. So we cannot integrate this. This computation here is not correct. We cannot just integrate over that infinite region here. Anyway, it is the last example. And for now, and then tomorrow we meet in class at a regular time.